Tonight, we're going to follow a beam of light into one of the most dangerous places the universe has ever built. Not a battlefield or a radioactive wasteland, but the heart of a supermassive black hole so violent it can outshine entire galaxies. This is not a quiet corner of space. This is cosmic demolition running at full power. Picture a quasar. A galaxy with its central black hole switched all the way on. Around it, an accretion disk of gas and dust spirals inward, heated to millions of degrees. From the poles, twin jets of particles blast out at nearly the speed of light, drilling through the galaxy and into intergalactic space. X-rays, gamma rays, and ultraviolet radiation pour out in a continuous storm, a wind intense enough to sterilize whole systems of planets thousands of light years away. In that kind of environment, nothing fragile is supposed to last. No calm gas clouds, no gentle star-forming nurseries, no tidy, orderly structures tracing elegant orbits. The standard picture says the region near a quasar's core should be chaos, shredded matter, shock fronts, and radiation pressure so extreme it blows away anything that even tries to organize. So when James Webb pointed its infrared eyes at one of these monsters, scientists expected to map destruction, measure how the black hole scours its host galaxy, refine models of how these engines shut down star formation and reshape the large-scale structure of the cosmos. No one predicts peace in a place like this, but that is not what the spacecraft saw. Through the dust, within just a few light years of the event horizon, Webb resolved something that looks disturbingly like order. A coherent signal, structured light, patterns that suggest gas is not only surviving, but cooling, rotating, and perhaps even collapsing into new stars right next to the very object that should be tearing everything apart. Think about the contrast. Humanity spent decades designing and launching this observatory, a mission built to look more than 13 billion years into the past, toward the first galaxies beyond our solar system's familiar neighborhood. Yet the same telescope is now picking out features only light years from a black hole that weighs billions of suns and radiates more power than all the stars in its galaxy combined. Before we get started, hold that image, a region that should be pure annihilation, quietly glowing with hints of creation. No one expects a star-forming ring hugging the edge of a quasar's glare. Absolutely no one anticipates a stable, rotating structure where theory says radiation should shred every boundary. By the end of tonight, you're going to understand what Webb actually saw, why that signal shouldn't be there, and how this single observation could force a rewrite of how black holes grow, how galaxies evolve, and where the universe allows complexity to survive. Now, let's begin. Before we get started on what Webb actually discovered, the danger of this black hole has to be clear. Not cinematic danger, real, quantifiable, astrophysical threat. In space, most dangerous is not about how scary something looks. It's about how much energy it can dump into its surroundings, how far that influence reaches, and how completely it can erase complexity inside a galaxy. Tonight, we're going to stand next to a monster that wins on every metric that matters. Extreme mass, extreme light, extreme violence. This is an ultra-luminous quasar, a hyperactive active galactic nucleus with a central black hole weighing in at billions of suns. In a region smaller than our solar system, it is emitting more energy than entire normal galaxies spread over hundreds of thousands of light years. That power is not gentle. The accretion disk is a maelstrom of plasma spiraling in at a significant fraction of light speed, converting gravitational energy into radiation with brutal efficiency. The output slams into the surrounding gas as an intense radiation field, a solar wind on steroids, pushing, heating, and stripping material out of the galaxy's inner regions. The boundary between near the black hole and the rest of the system is not a clean line. It's a blast zone. Earlier generations of telescopes could only see this object as a blinding point. Hubble showed a brilliant core drowning out the host galaxy with broad emission lines in its spectrum that told scientists gas was whipping around at thousands of kilometers per second. Chandra and other X-ray observatories revealed a hard, energetic glow and hints of powerful outflows. Ground-based observatories using adaptive optics saw distorted structures and tidal features, but the inner few light years remained hidden behind dust, distance, and glare. So the picture was simple. A central engine so bright it carved out cavities, jets so strong they could punch straight through intergalactic space for millions of light years, carrying magnetic fields and high-energy particles far beyond the visible galaxy. Tidal forces near the core, strong enough to tear entire stars into streams of gas. Radiation fields intense enough to strip electrons from atoms over vast volumes, sterilizing potential planets long before life could begin. No one predicts a calm, ordered environment there. Standard models say the feedback from such a quasar should blow gas out of the central regions, shred disks, and quench star formation. You expect chaos, turbulence, and emptiness in the immediate kill zone. The closer you get to the event horizon, the less room there should be for anything fragile, rotating, or long-lived. And yet, Webb's infrared eyes are about to look straight through the dust and glare, resolving scales only light years from the brink. Where theory says there should be only destruction, absolutely no one anticipates seeing something that looks eerily stable, almost organized, holding its shape right inside the blast furnace. That is the contradiction waiting on the other side of the data. So what, exactly, should be waiting there in that blast furnace? In the standard picture, the inner few light years of an extreme quasar are not a neighborhood. They are a demolition zone. Matter spirals in toward the event horizon, crushed into a thin, incandescent accretion disk where temperatures soar high enough to strip atoms and drive a blinding glare across space. Closer in, gravity and rotation try to organize the flow into a disk, but the more that disk feeds the black hole, the more energy it releases. That energy does not stay quiet. It erupts as radiation pressure, as a relentless photon wind, and as powerful outflows that tear through the surrounding system. Designed on paper, this region looks simple: a hot inner disk, a chaotic halo of shredded gas, and then, further out, a galaxy trying to exist. Now, let's begin to push that picture. In these ultra-luminous quasars, the light from the central engine can outshine billions of suns. On human scales, it is like putting a snowflake factory inside a steel mill furnace and turning the heat up. No one expects delicate, cold clouds to survive there. No one predicts ordered rings of gas quietly rotating in the glare. The feedback from the black hole should blast apart any attempt at calm structure. Dense, cold gas is especially fragile. To make stars, gas must cool, condense, and stay shielded from intense radiation long enough to collapse. Within a few light years of a quasar that bright, theory says the opposite happens. Ultraviolet and X-ray photons slam into atoms, heat them, ionize them, and drive them outward. Star formation should be quenched like trying to freeze water in the exhaust of a rocket engine. This is where James Webb changes the game. Its infrared eyes do not just see light, They decode motion, temperature, and composition. Narrow emission lines reveal gas moving in coherent patterns instead of random turbulence. Rotational signatures in those lines can trace a disk or ring showing one side moving toward us, the other side moving away, like a record spinning in the dark. Dust temperatures measured by Webb's instruments can separate scalding, near-disk material from cooler, more distant regions where stars might still be forming. So here is the core contradiction. If JWST's data are right, then there are signals of ordered rotation and surprisingly cool gas right inside a zone that should be pure destruction. Either the standard models of black hole feedback are missing something huge about how energy couples to gas, or this particular object is doing something fundamentally new that has never been seen at this scale. Tonight, we're going to treat that as a test. By the end of tonight, you're going to understand why this detection should not be there at all. And to get there, the next part of this mission walks through 7 specific pieces of Webb evidence, each more unsettling than the last, until the impossible structure near this monster black hole stops looking like a glitch and starts looking like a challenge. The first clue hides in the narrowest lines of all. That phrase, the first clue hides in the narrowest lines of all, is not random. If you're still here, listening for clues in spectral lines near a monster black hole, you are not a casual space viewer. You are the kind of person who wants to understand the deep structure of the universe, not just watch pretty images drift past. This channel exists for that exact reason. Most headlines treat James Webb as a fire hose of isolated surprises. One day a record-breaking galaxy, the next day an eerie ring, the next a strange wind near some distant quasar. But the real mission is longer and stranger. Each detection is not a disconnected miracle, it is a data point in a story where our picture of the cosmos keeps being overturned, refined, then overturned again. Tonight, we're going to follow Webb not as a single press release, but as a spacecraft embedded in a decades-long effort to map how black holes grow, how galaxies evolve around them, and where the boundaries of current theory actually crack. The same instruments that can pierce dust around a supermassive black hole and reveal structures within a few light years of the event horizon are also rewriting ideas about the early solar system, rogue planets, and the chemistry of worlds beyond. It is one continuous narrative of models meeting reality. Before we get started on the next piece of that narrative, a quick request. If long-form, carefully paced dives into strange data and broken models are valuable to you, taking a second to like this video or subscribe is not just a formality. It directly tells the algorithm there is an audience for content that does not rush past the hard parts. No one expects a platform optimized for short clips to reward 40-minute breakdowns of black hole spectra, but that signal helps this reach more people who think the same way you do. Here is the contrast. Without that support, the pressure is always to compress. Mention the discovery, flash the image, move on. With it, there is time to slow down over a single spectral line to explain why a narrow feature near a deadly quasar might mean cold gas, where only chaos should exist, and to follow that thread through the whole system. The more this mission is backed, the more hours can be spent unpacking feedback, accretion, and the strange regions where destruction and creation overlap. Now, let's begin the next step, because to understand why this one observation is so shocking, the story has to rewind, not just to the launch of James Webb, but to the first hints that black holes could do something no one predicts, light up the universe instead of simply swallowing it. So to see why that is so radical, the story has to roll back to a very different night in space science. Before we get started with James Webb's razor-sharp infrared vision, picture the 1960s. Giant radio dishes scanning the sky, picking up powerful signals from nowhere in particular. No planets, no obvious galaxies, just anonymous points that screamed in radio waves. On photographic plates, those radio positions lined up with what looked like ordinary stars. Tiny, featureless, unremarkable. Then spectra came back with emission lines in all the wrong places. The only way they made sense was if those lines were redshifted by enormous amounts, meaning these quasi-stellar radio sources were billions of light years away. The boundary between imagination and reality snapped. If they were that distant, they were outshining entire galaxies from a region no larger than our solar system. Tonight, we're going to stand where those scientists stood and ask the same question. What engine in the universe can be that bright, that compact, and that persistent? Nuclear fusion in stars cannot do it. No cluster of exploding stars can sustain it. The only reservoir of energy big enough is gravity itself, released as matter spirals into something incredibly dense. That is where the idea of supermassive black holes stepped out of pure theory. Take a black hole with millions to billions of solar masses, surround it with an accretion disk of infalling gas. As that gas falls inward, it heats to millions of degrees, blasting out radiation across the spectrum and driving powerful winds and jets. Suddenly, the impossible luminosity of quasars becomes not just plausible, but expected. At first, no one expects nature to actually build these monsters. Black holes are supposed to be mathematical curiosities, not central engines of galaxies. But observations keep piling up. Safe-at galaxies show bright, variable cores. Radio galaxies launch jets that stretch hundreds of thousands of light years. X-ray space missions find compact, ferocious sources right at galactic centers. Piece by piece, the pattern locks in. By the end of tonight, you're going to understand how that pattern got a name. Active galactic nuclei. Different costumes, same engine. Safe-Earths with bright optical cores, radio galaxies with colossal jets, quasars blazing from the early universe. Change the viewing angle, the amount of dust, the feeding rate, and the same central black hole can look wildly different, but the physics is unified. Now, let's begin to connect this to the present. The most dangerous black hole under Webb's gaze is not an outlier from this family. It is the extreme endpoint, an AGN turned up to maximum, where the accretion disk, the jets, and the surrounding winds are all operating at full throttle. Every process that Unified Model describes is pushed to its limits, right up against the edge of what current theory says should be possible. And that is where James Webb walks in, stares directly into the glare, and discovers that something at this boundary refuses to behave. Before we get started with what James Webb actually discovered, there is a model, a picture that has guided scientists for decades whenever they look at a feeding black hole and try to understand what is happening in that glare. In the standard view, gas does not plunge straight in, it spirals. As it falls toward the event horizon, it spreads into a thin, rotating accretion disk, a kind of cosmic whirlpool. Friction between neighboring rings of gas and magnetic turbulence threading through the plasma grind away orbital energy and convert it into heat. The closer you get to the center, the hotter it becomes, until the inner disk blazes across the spectrum, from X-rays down to infrared. That light is not just a passive glow, it pushes back. Every photon streaming out from the disk carries momentum. And when those photons slam into surrounding gas, they exert radiation pressure. In the most extreme quasars, the combined power of that light, plus the solar-scale winds driven off the disk, can literally shove gas out of the galaxy's core. This is feedback, the black hole's own emission throttling its fuel supply and reshaping the central regions of the system. Tonight, we're going to lean on one crucial number that emerges from this interplay of gravity and light, the Eddington limit. At this limit, the inward pull of the black hole's gravity on infalling matter is exactly balanced by the outward push of radiation. Accrete faster than this in a steady state, and the outgoing light should blow the gas away. Accrete slower, and gravity wins, drawing more material in. By the end of tonight, you're going to understand why that balance is supposed to act like a hard ceiling on how fast a black hole can feed. Now, let's begin to zoom in on the inner few light years around a monster quasar, one of the most dangerous black holes in the observable universe. Simulations that crank the accretion rate up near the Eddington limit predict chaos. Supersonic inflows crash into outflows, magnetic fields twist and reconnect. Gas is shock-heated, stirred into violent turbulence, and blasted outward in thick, multi-phase winds. In that environment, clouds are shredded faster than they can cool. Ordered structures do not last. The expectation is clear. In the regions where James Webb is now resolving individual clumps of gas, the models predict a storm, hot, ragged, transient flows, not neatly arranged rings. No one expects cold, dense gas to survive there long enough to settle. No one predicts that star-forming pockets could quietly orbit inside that maelstrom. Absolutely no one anticipates seeing a clean, almost architectural ring where theory demands only destruction. And that is the tension. If the standard accretion disk and feedback picture is even roughly right at these extremes, then what James Webb appears to be seeing around this black hole should be impossible, or at least vanishingly rare. So what is that ring really made of, and how could it exist at the very boundary where gravity and radiation are locked in combat? To answer that, you have to look at the only machine in existence built to stare straight through cosmic hellfire and not blink. Now, let's begin. The James Webb Space Telescope is not just a bigger Hubble, it is a cold, infrared-optimized observatory parked 1.5 million kilometers from Earth at a gravitational balance point called L2. Out there, shielded from the sun and the warm glow of our own solar system, it can cool its mirrors and instruments so far that even faint, red-shifted light from the early universe becomes visible. That cold is not a luxury. It is the whole trick. The most dangerous black holes sit in galaxy cores wrapped in dust and gas, glowing in high-energy radiation that optical telescopes mostly miss or have blurred into anonymity. Hubble sees the glare, Webb sees the structure hidden inside the glare. By the end of tonight, you're going to understand why that difference matters. Start with its eyes. NIRCam, the near-infrared camera, takes in light just beyond deep red, where stretched starlight and heated dust shine. MIRI, the mid-infrared instrument, pushes farther into wavelengths where dust grains, complex molecules, and warm ionized gas leave distinctive fingerprints. These are not just cameras. They are spectrographs that can slice that light into thousands of narrow colors, letting scientists read temperature, composition, and motion in regions that once looked like formless smoke. Before we get started on what Webb saw, notice what it can resolve. That gold-segmented mirror is 6.5 meters across, designed for a 5 to 10-year mission to map the distant universe. It can pick out features only a few light-years across in galaxies hundreds of millions of light-years away. Where older observatories recorded a single blur around an active nucleus, Webb can separate knots, lanes, and rings of material orbiting in the black hole's immediate neighborhood. For active galactic nuclei, that resolution in the infrared is everything. The dust near the black hole absorbs X-rays and ultraviolet light from the accretion disk, then re-emits that energy as infrared glow. In optical light, you see a harsh point source and chaos. In Webb's bands, that same region becomes a map. Cooler, outer dust. Hotter, inner walls, cavities carved by jets, and dense clumps where gravity is winning against radiation. This is where the pattern interrupt hits. Theory says the inner few light years around a hyperluminous black hole should be stripped, shredded, and violently unstable. Yet, with NOAACAM and MIRI tuned to the right wavelengths, this single spacecraft can now trace coherent structures right up to that boundary where gravity and radiation are locked in combat. No one expects to see a quiet, ordered ring there. No one predicts symmetry in a place defined by extremes. And absolutely no one anticipates that when James Webb finally looks this deeply into the most dangerous black hole's neighborhood, the data will hint at survival, not just destruction. That is the observation coming next. That observation coming next does not happen by accident. To catch survival in the jaws of destruction, scientists have to be picky. In a sky filled with millions of active galaxies, they went hunting for the one black hole so violent, so luminous, that James Webb's infrared eyes could turn sheer danger into clean, testable data. The original plan is simple. Use decades of surveys to build a menu, X-ray catalogues from Chandra and XMM Newton, radio maps from the VLA, optical spectra from Sloan and other sky scans, each entry a different kind of monster in the distant universe. Then, from that chaos, select only the brightest, most extreme quasars, where the central engine drowns out the host galaxy, and the solar wind of the central accretion flow pushes physics to the edge. Most candidates are impressive. A few are terrifying. One stands out. Its core blazes with more power than an entire Milky Way-sized system. Its jets scream out in radio like twin lances of energy, and earlier spectra show emission lines so broad and skewed that even seasoned observers pause. The luminosity brushes up against theoretical limits, the so-called Eddington boundary, where radiation should blow material away faster than gravity can pull it in. Prediction meets observation, and they do not line up. Previous X-ray data suggest a black hole mass of tens of billions of suns. Optical measurements hint at a smaller engine with an absurdly high feeding rate. Radio imaging insists on ultra-relativistic jets that should clear out the surroundings. No one expects all three to be true at once. This object becomes a natural stress test for every model of accretion, feedback, and galaxy evolution. Before we get started with Webb, there is one more twist. Infrared surveys already show heavy dust veiling the galactic core, as if the central region is wrapped in a cosmic smokescreen. That is exactly where JWST excels. NIRCam can cut through the dust to map the innermost starlight. MIRI can trace warm molecular gas and tiny dust grains glowing in the mid-infrared. Together, they can separate stars from gas, gas from jets, jets from the blinding heart of the accretion disk. So the observing strategy is aggressive. Multiple instruments, overlapping filters, deep integrations. Images to resolve structures only a few light years across. Spectra to decode velocities, temperatures, and chemical fingerprints. By the end of tonight, you're going to understand how this mission turned a distant point of light into a dissected, three-dimensional environment. Now, let's begin. Teams expect turbulence, shredded clouds, perhaps a warped disk on the edge of disintegration. They plan to refine models of chaotic inflow and explosive outflow to measure exactly how a black hole this dangerous sculpts the space around it. But when the first calibrated frames appear on their screens, a quiet, sharply defined feature near the core makes several groups stop mid-sentence and ask the same question. Wait, is that real? What they expect to see is chaos. A blinding pinprick where the active galactic nucleus overwhelms everything, bleeding through the detectors, surrounded by clumpy, shredded dust and warped starlight from a host galaxy being torn apart at the seams. For a black hole this violent, the inner few light years should look like a demolition zone, not a blueprint. Before we get started on the surprise, picture the raw frames arriving from JWST. At the center, a saturated spike of light, the AGN so bright it behaves like a defect in the image. Around it, faint, smeared structure, distorted by the telescope's optics and by the glare of the core. This is what scientists sign up for when they point a space observatory at the most dangerous engine in the system of that galaxy. So they do what high-contrast imaging teams do best. They build a model of the central point source using nearby stars and the telescope's precisely measured point spread function as a template. Then, numerically, they place an artificial mask over the black hole's glare. It is like holding up your hand to block a car's headlights so you can finally see the dark road, the trees, the boundary markers beyond the beam. Subtract the light, recalibrate, repeat across filters. The expectation is simple. Once the central spike is removed, the remaining pattern should be messy. Filaments of gas, irregular dust lanes, maybe hints of tidal streams from disrupted star systems, all jumbled together by the black hole's gravity and the solar system-sized winds it drives into space. That is not what appears. When the processed image stabilizes, a quiet, coherent structure emerges where there should only be turbulence. A ring, or at least a sharply defined, disk-like loop of emission at a specific radius from the core, not hugging the event horizon, but not safely distant either. Its brightness is not uniform, it ripples, with bright knots and dim gaps that look suspiciously like organized rotation or clumping, not random debris. Pattern interrupt. This is not a single hot pixel or a glitch in one filter. The feature persists when the team switches from one infrared band to another. It shows up in multiple exposures taken on different days, with different spacecraft roll angles, and it lines up with where certain infrared emission lines from ionized gas and warm dust are strongest. No one expects that kind of geometric elegance this close to a monster. Now, let's begin to frame the real problem. By the end of tonight, you're going to understand why this ring keeps theorists awake. In standard models, the black hole's radiation and jets should blast this zone clean, stripping gas, shredding dust, and shutting down star formation. Yet the image hints at a stable, or at least long-lived, structure. Is this a dense ring of gas feeding the core, a dust disk surviving in a narrow safe zone, or even a band of newborn stars orbiting in a place where absolutely no one anticipates anything gentle can endure? Astronomers do not fall in love with the first weird thing they see on a screen, especially not when it appears right next to one of the brightest, most dangerous black holes in the known universe. The first reaction is suspicion. That ring might not be a ring at all. Near a blinding active galactic nucleus, the safest assumption is that the telescope is lying to you. It could be a processing artifact from the way the image is reconstructed. It could be a diffraction pattern from JWST's segmented mirror, the same physics that creates those famous six-pointed stars around bright objects. It could be a calibration error, a ghost of the instrument, rather than a real boundary in space. So, before anyone starts rewriting models of how black holes carve up their galaxies, the team does something much less glamorous. They try to make the ring disappear. Now, let's begin with the most basic test. Does this thing look like anything in the telescope's own optical fingerprint? Every space telescope has a point spread function, or PSF, a detailed map of how a perfect point of light should spread out across the detectors. For JWST, that PSF includes the hexagonal mirror pattern, the diffraction spikes, the subtle halos and ripples that appear around bright sources. The scientists pulled those PSF models along with real calibration images of bright stars and overlaid them on the black hole image. If the ring lined up with one of those expected structures, the mystery would be solved in the least exciting way possible. It didn't. The spikes matched, the inner glare matched, but the ring sat off those patterns like a separate stubborn feature. So the checks escalated. Different filters first. If the ring were an artifact tied to a specific wavelength, it should change shape or vanish as the team switched from one infrared band to another. It stayed. Different roll angles next. Rotate the entire spacecraft. Let the optics spin relative to the sky. Instrumental ghosts rotate with the telescope. Real astrophysical structures stay locked to the galaxy. The ring held its position. Then came the software gauntlet. Independent reduction pipelines built by different groups processed the raw data from scratch. Different algorithms, different assumptions, different ways of subtracting the blinding core. By the end of tonight, you're going to understand why this matters. If every path through the data leads to the same faint loop, the odds of a fluke drop fast, still there. They even pulled control targets, other bright AGN observed in similar modes, with similar brightness and similar exposure times. No one expects perfection here. If this were a systematic effect, those galaxies should also wear matching rings. They didn't. The boundary around this black hole refused to be a glitch. It survived every filter, every rotation, every comparison. No one predicts that outcome from standard models. Yet there it is, an apparently real structure parked in a region where the black hole's radiation should erase order. Tonight, we're going to follow what that means, because if this ring is genuine, the simple picture of nothing survives this close is already broken. And the next observations are about to push it even further. So the next move is obvious. If this ring is really sitting in the jaws of the most dangerous black hole in the field, scientists need to know exactly where it lives. Not just close or nearby, but how many light years out, how many event horizons away from the point of no return. Now, let's begin with the image itself. JWST doesn't hand over a ruler in light years, it hands over angles, fractions of an arcsecond measured on a detector, pixel by pixel. To turn that into real distance in space, astronomers start with the galaxy's redshift, the way its light has been stretched by the expansion of the universe. From that redshift, cosmology gives a distance, and from that distance you get a conversion. So many light years per arcsecond, so many light years per pixel. For this black hole's host, that scale works out to a frightening number. Each JWST pixel near the core spans perhaps a few light years. When the ring is traced and its apparent radius is measured, the answer drops out. This structure is orbiting only a few light-years from the central monster, not thousands, not the quiet outskirts of the galaxy. It is embedded right where the black hole's gravity and radiation dominate the entire core. To feel how close that is, bring it home. The outer edge of our solar system, the region where the sun's wind fades into the interstellar medium, is only a fraction of a light-year away. Proxima Centauri, the nearest star, is about 4.2 light-years out. This ring sits at a distance from its black hole that, in scaled-down terms, would put whole clouds of gas where our neighbouring stars live. In the Milky Way's own centre, gas clouds orbit the central black hole on scales of a few light-years, but they are constantly shredded, shocked, and heated. By the end of tonight, you're going to understand why that comparison is so unsettling. Theoretical models divide this region into zones. Closest in is the blazing inner accretion disk, where gas spirals down and converts gravitational energy into radiation. Farther out, a puffier, dusty torus is expected to wrap around the system, and beyond that, powerful outflows and winds should carve channels through the galaxy's core. On paper, the radius JWST is probing lands right on that boundary. It is where the inner disk hands off to the torus, or where the torus dissolves into the larger scale wind. No one expects a calm, narrow ring to survive there. Gas should be doing one of three things: plunging inward at high speed, being blasted outward by radiation pressure, or being shock-heated into a turbulent haze. Yet the image shows something that looks settled, ordered, long-lived. Before we get started on what that implies, remember this radius, because the next measurements will test whether this ring is defying gravity, defying radiation, or forcing an entirely new picture of how black holes shape their host galaxies. That ordered ring is not just a pretty structure on a JWST poster, it has a voice. And that voice is hidden in its light. James Webb did not only take a sharp infrared picture and call the mission complete, it opened its spectrographs and split the ring's glow into thousands of colours, turning a single eerie halo into a barcode of physics. Now, let's begin to read what that barcode says. In those spectra, scientists discovered bright hydrogen recombination lines, the fingerprints of electrons snapping back onto protons after being ripped away by intense radiation. These are not quiet, neutral clouds drifting through space. They are being ionized, stripped, and then allowed to cool just enough for hydrogen to reassemble and shine. Alongside hydrogen, there are lines from ionized oxygen and neon, elements forged in earlier generations of stars and now lit up by the black hole's furious engine. The pattern matters. If the ring were just a random shell of debris inside the galaxy, the emission would look messy, with broad, chaotic features. Instead, the lines are clean and distinct. Certain oxygen lines appear stronger in the inner edge of the ring. Neon glows more fiercely where the radiation field is hardest. This is a system under intense, structured illumination, not a cloud being shredded at random. Tonight, we're going to follow those lines one step further because their shapes are just as revealing as their wavelengths. Each line is not razor thin, it is broadened and shifted, smeared out by motion. On one side of the ring, the hydrogen and oxygen lines are systematically red-shifted, nudged to longer wavelengths. On the opposite side, the same lines are blue-shifted, pulled to shorter wavelengths. This is not turbulence. It is a signature of rotation. One half of the ring is moving away, the other half is coming toward the spacecraft, tracing a coherent orbit around the central black hole. By the end of tonight, you're going to understand why that is so alarming. Near the most dangerous object in this galaxy, where theory predicts violent outflows and chaos, JWST is seeing an organized, rotating structure that behaves more like a galactic disk than a doomed gas cloud. Then there is the quiet surprise no one expects near such a lethal core. Mixed into the emission from hot gas are hints of warm dust and molecular features, the spectral traces of complex molecules surviving in the glare. Some lines resemble those seen in star-forming regions elsewhere in the solar neighborhood of our own galaxy. Polycyclic aromatic hydrocarbons, warm silicate dust, and continuum shapes that look suspiciously like dust heated by young massive stars. No one predicts active star formation this close to a quasar-level black hole. Absolutely no one anticipates a ring that is not only orbiting, but possibly giving birth to new suns in the teeth of a relativistic wind. So the spectra do not just say, there is gas here. They whisper that this ring is dynamic, organized, and maybe long-lived. Which leaves a deeper question hanging at the boundary of what models can explain. How did such a fragile, star-forming ring assemble and survive in the blast furnace of the most dangerous black hole we know? So the spectra do not just say there is gas here. They whisper that this ring is dynamic, organized, and maybe long-lived, which forces a brutal reframe. In the shadow of a black hole that can shred stars, strip atoms, and flood space with lethal radiation, James Webb is seeing signs that stars might be forming. That is not a poetic exaggeration. That is the emerging physical picture near one of the most dangerous engines in the known universe, where theory says fragile structures should be erased. The data hint at assembly, creation, not just annihilation, written into the light. To feel how wrong that is, imagine a nuclear blast zone. At the center, temperatures vaporize metal, shockwaves flatten cities. Now picture walking right up to the inner rim of that destruction and finding a calm, fertile oasis. Clear water, young trees, seeds quietly sprouting in the glow of the fireball. That is what this looks like in space. A cool, structured ring on the inner edge of a relativistic wind. Before we get started on explanations, it helps to pin down why scientists are so unsettled. This does not look like a random clump of debris briefly passing through. The gas is rotating in an ordered way, as if locked into an orbital lane. The emission lines are narrow and specific, tracing dense knots where hydrogen and heavier elements are cooling and clumping. The dust temperatures are relatively low and surprisingly uniform, more like a settled, star-forming ring than a chaotic spray of wreckage. Prediction versus observation could not be clearer. Models say an ultra-luminous black hole should carve out a cavity, heating and blowing out gas so violently that star formation is quenched. James Webb looks, and instead of emptiness, it discovers a ring that behaves like a nursery. No one expects a stellar cradle this close to a cosmic executioner. No one predicts a structured, potentially long-lived system orbiting in the blast furnace. This is where the intuition about black holes has to change. They are not just cosmic drains that delete matter from the story. Their outflows and radiation can also push on gas, compressing it, driving shock fronts that, under the right conditions, ignite star formation. Galaxies across space show rings and arcs of stars that were probably triggered by this feedback, but almost always those rings live farther out, at safer distances, where the balance between pressure and gravity is less extreme. Here, that balance is unfolding almost on the doorstep of the event horizon. Tonight, we're going to treat this ring as a laboratory at the boundary between destruction and creation. By the end of tonight, you're going to understand how a black hole that can sterilize entire solar systems might also be quietly helping to build new ones, and what that paradox tells scientists about how galaxies grow. Now, let's begin to ask the uncomfortable question: how do fragile stars assemble in a place that should erase them faster than they can form? The uncomfortable answer begins with something that should not be there at all. Very close to this quasar's heart, James Webb resolves a ring, not a vague glow, a sharply defined, rotating ring of gas and dust hanging just a few light years from a black hole that outshines entire galaxies. In Webb's NIRCam images, it appears as a narrow, infrared bright band. Spectroscopy shows it has a radius of only a few light years, a thickness a fraction of that, and a mass comparable to tens of millions of suns bound into a single, coherent structure. And it is not just sitting there, it is moving with terrifying precision. The spectral lines are split and shifted, one side of the ring racing toward the spacecraft, the other side racing away. From those Doppler shifts, scientists infer orbital speeds of hundreds of kilometers per second, fast enough to circle the black hole in less than 1,000,000 years, yet ordered enough that the ring looks like a calm traffic lane in the middle of a gravitational hurricane. Before we get started on why that is a problem, remember what every model said this region should look like. Near an active galactic nucleus this bright, the expectation is chaos. Radiation pressure from the blazing accretion disk, plus powerful winds and jets, should shred incoming gas into clumps, filaments, and turbulent flows. Simulations predicted a frothing, clumpy medium with no long-lived, coherent rings surviving for many orbits, designed for destruction, not architecture. That was the picture. Yet here, in the glare of the most dangerous black hole in this system of galaxies, Webb sees the opposite. A ring that is not only intact, but dynamically cold enough that its rotation dominates over random motions. No one expects a structure like this at these luminosities. No one predicts that gas can settle into a neat, quasi-stable configuration while being blasted by X-rays and ultraviolet light strong enough to sterilize solar systems far beyond its radius. The ordered motion is the key. To line up into a ring, the gas must have orbited many times, trading chaotic kinetic energy for a smoother, flattened flow. That takes time. This is not a one-off tidal disruption event, not the shredded remains of a single unlucky cloud still in the act of falling in. It looks more like a persistent circulation pattern, a gravitationally guided ring road feeding and perhaps regulating the black hole. That alone challenges a core assumption. At these extremes, theory says radiation pressure and outflows should always dominate over gravity on this scale, pushing material out faster than it can settle. Yet the ring's very existence says gravity has quietly won a local battle, carving order out of what should have been pure feedback. Discovery 1 is simple to state, but profound. There is an ordered, rotating ring of gas and dust in a place where models said only chaos should reign. Tonight, we're going to follow that ring inward and outward and see what else it is quietly breaking. Now, let's begin to ask the next question. If the gas can organize itself here, what else in this deadly core is more structured than anyone dared to imagine? If the ring were just gas calmly orbiting the black hole, that would already be strange. But JWST is whispering something far more radical. This ring is not only surviving, it may be giving birth. Before we get started, remember where this is. This is not some quiet spiral arm in a distant, gentle galaxy. This is a narrow band of material a few light years from a quasar core, so bright it outshines entire galaxies, a place where the radiation wind should strip electrons off atoms and tear molecules apart. No one expects a cradle of stars here, yet the spectra say otherwise. NIRCam and MIRI do not just see a smooth glow. They see the fingerprints of ultraviolet heated dust re-radiating that brutal energy in the mid-infrared. The continuum shape across those wavelengths looks like dust wrapped around hot, young stellar populations, not just gas lit by the active nucleus. On top of that, emission line ratios in hydrogen, oxygen and neon are skewed in a way that, in calmer regions of space, is the textbook sign of recent star formation. Astronomers have spent decades calibrating these diagnostics in nearby galaxies, measure how bright certain lines are, compare them to the underlying continuum, and a number drops out, a star formation rate. When they run those same tools on this ring, they do not get zero. They get a non-trivial flow of new stars, perhaps a few suns' worth of material per year, freezing into stellar cores, concentrated in a band that could fit inside the inner solar system. By the end of tonight, you're going to understand why that number is so unsettling. Standard theory says that as gas approaches a hyperluminous, active galactic nucleus, the radiation pressure and X-ray and ultraviolet photons should photo-evaporate dense clouds, boiling them into diffuse plasma. The gas cannot cool, cannot fragment, cannot collapse. The closer the gas gets, the more the black hole sterilizes its surroundings. There is a loophole. In some simulations, when the central engine launches powerful outflows, those winds slam into surrounding gas, compressing it like a piston. Under the right conditions, that shock can actually trigger star formation in shells and arcs tens or hundreds of light years out. No one predicts what JWST is hinting at here, a sharply defined, rotating ring of triggered starbirth right on the edge of the danger zone, bathed in a radiation field that should erase those clouds faster than they can collapse. So, what is this ring? A freak coincidence of geometry and timing, a tiny exception carved by finely tuned conditions around one monster? Or has this mission just exposed a whole hidden mode of black hole-induced star formation operating in the most extreme systems, right where absolutely no one anticipates creation to win over destruction? To test that, scientists turned to the one thing this mission can do better than any other: read the motion of gas directly from its light. Not just where it is, how it moves, because hidden inside every spectral line is a fingerprint of velocity, turbulence, and temperature. Now, let's begin. When gas orbits in an orderly disk or ring, its motion is dominated by rotation. On one side, the spectral lines are shifted slightly toward the blue, on the other, toward the red. Map those shifts across space and you recover the rotation curve, the clean, almost clockwork spin around the black hole. But the width of those lines, how fat or thin they are at each position, tells a different story. The random motions, the chaotic jostling, the internal storm. If the region is turbulent, each tiny parcel of gas races around at different speeds and directions on top of the overall rotation. That spreads the line out. Narrow lines mean calmer gas, with lower random velocities. Broad lines mean a maelstrom. Tonight, we're going to follow those widths as they trace invisible weather in one of the harshest environments in space. Every major feedback model said the same thing. At this radius, under this radiation field, with this kind of AGN wind ploughing through the system, the ring should be stirred up. Simulations predicted broad, ragged lines, velocity dispersions that scream of shock fronts, shear, and constant reheating. No one predicts a quiet zone here. But that is not what Webb discovered. The ring is moving. Yes, it orbits fast, in a deep gravitational well. Yet, on top of that ordered motion, the spectral lines are surprisingly narrow. The inferred turbulence is modest, closer to what is seen in normal star-forming regions of calm galactic disks than in gas being battered near a hyperactive nucleus. Where the models expect a blender, the data shows something closer to a gently stirred pool. Step just outside that ring, though, and the story changes violently. In the outflow regions, further from the core, but directly in the path of the AGN wind, the same lines balloon in width, velocities spike, profiles split, and skew. There, the kinematics look like the simulations promised, chaotic, heated, shredded by the black hole's energy. The contrast is stark. A relatively calm, dynamically cool ring wrapped inside a broader storm that looks every bit as dangerous as advertised. That contrast matters. Lower turbulence means gas can radiate away its heat more efficiently, sink to higher densities, and fragment under its own gravity. In simple terms, calmer gas can turn into stars. By the end of tonight, you're going to understand why this makes the ring not just a survivor, but a fertile cradle in a place theory reserved for sterilization. So if the ring is cool, ordered, and quietly forming new suns, what does that say about how the black hole's power is being channeled? Has the energy been redirected, collimated, sculpted into safe lanes and lethal beams? And if such delicate structure can hide inside this apparent calm, what else might be waiting there, just beyond our current resolution? To answer that, the usual mental picture has to be broken. The image of a black hole as a cosmic vacuum cleaner or an executioner swinging a gravitational axe is simple. It is also wrong in a very important way. Tonight, we're going to replace it with something far stranger. Imagine this monster not as a single hungry mouth, but as a gardener in a very violent garden. In one hand, a leaf blower. In the other, a high-pressure sprinkler. Its jets, winds, and radiation are not just killing everything nearby, they are rearranging where anything can grow. The feedback from an active black hole is not gentle. Relativistic jets spear through space at nearly light speed. X-rays and ultraviolet radiation flood the surrounding gas. Powerful winds, driven by the blazing accretion disk, slam into clouds that drift too close. The expectation is simple. All this energy should sterilize the region, strip out the gas, and shut down star formation within light years. But feedback has a second mode. When those outflows hit gas at the right angle and at the right distance, they do not just blow it away. They compress it. They squeeze vast, cold reservoirs into thinner, denser filaments. And dense gas does one thing in this universe: it collapses into new stars. By the end of tonight, you're going to understand why the same blast that quenches one region can ignite another. Think about what JWST is actually seeing in this ring. The innermost zone looks scoured, as if the leaf blower has been running at full power, clearing out the central few light years. But at a very specific radius, the pattern flips. There, the black hole's outflows appear to slam into orbiting gas, pile it up, and create a narrow annulus where temperature, pressure, and rotation all line up. Too close, and the radiation tears clouds apart. Too far, and the wind is weak, the gas stays diffuse, and nothing collapses. No one predicts a perfect, star-forming ring right in the crosshairs of the most dangerous engine in the galaxy. Yet that is what this system is advertising. A thin, luminous boundary where destruction on the inside becomes creation on the outside. The idea that black holes could both quench and trigger star formation is not new. Some scientists have modelled this positive feedback for years, especially in simulations of young galaxies in the early universe. But seeing it carved this sharply, this close to a hyperactive nucleus, is different. It is not a soft, statistical trend across many galaxies. It is a single, defiant structure that should not survive there. Before we get started on what this means for galaxy evolution as a whole, there is an even more personal comparison to make. Our own Milky Way has a central black hole too, far quieter, far less extreme. If this dangerous gardener can sculpt a ring under such brutal conditions, what might our relatively calm central engine be doing to the solar neighbourhood around it? To see how extreme this monster really is, it helps to look home. Our own galaxy hides a supermassive black hole too, right at the centre, and compared to the JWST target, it looks almost polite. That central engine is called Sagittarius A. About 4 million times the mass of the Sun. A heavyweight by any measure, sitting 26,000 light-years away, quietly anchoring the Milky Way's gravitational architecture. Yet for all that mass, its current accretion rate is tiny. It's nibbling, not feasting. In most wavelengths of spacelight, the core of our system is dim enough that for decades scientists wondered whether it was even active at all. Zoom in with radio and infrared instruments, though, and the picture sharpens. Surrounding Sagittarius A is a circumnuclear disk of gas and dust, a clumpy, rotating ring a few light-years across. Inside that, orbiting in the black hole's deep potential well, are clusters of young, massive stars racing around at hundreds of kilometers per second. They live in an environment where tidal forces are fierce and the local radiation field is harsh compared to the solar neighborhood, yet somehow they formed there. This alone was once a puzzle. The expectation was simple. Get too close to a supermassive black hole and gravity tears molecular clouds apart before they can collapse. The reality near Sagittarius AI is more nuanced. Gas can pile up in the circumnuclear disk, cool, fragment, and trigger star formation surprisingly close to the boundary of real danger. By the end of tonight, you're going to understand why that earlier surprise suddenly feels almost tame. There are also scars in the sky that hint our black hole was far louder in the past. Giant gamma-ray bubbles ballooning above and below the galactic plane. X-ray echoes in surrounding molecular clouds. Together they trace at least one phase when Sagittarius A lit up, driving powerful outflows and winds through the inner galaxy. No one predicts a perfectly quiet history. The evidence shows a flickering engine cycling between active and quiescent states. Yet even at its peak, the Milky Way's core has never rivaled the ultra-luminous quasar now under Webb's gaze. Our centre is dim by quasar standards, thousands of times less luminous, with far gentler radiation fields and weaker accretion flows. Star formation near Sagittarius A happens in a regime where gas is stressed but not obliterated. That contrast is the key. Black hole. Adjacent star formation is not unheard of. Sagittarius A proves that disks and clusters can grow in the shadow of a central engine. But scaling that up to a system thousands of times brighter, where the black hole's wind and light should strip everything clean, is what makes the JWST ring so shocking. If similar rings are hiding around many luminous quasars, then tonight we're going to confront a bigger possibility. Black holes might not just shut galaxies down, they might also ignite new generations of stars, a common, underappreciated ingredient in how galaxies build themselves over cosmic time. Now, let's begin. The surprise is not just that the ring exists, it's what the ring is made of. JWST doesn't just take pretty images, it dissects light. Its spectrographs spread the ring's glow into thousands of wavelengths, like a barcode. From that barcode, scientists can read the chemistry of this space, estimating the metallicity, the abundance of elements heavier than helium in the gas and dust that circle this black hole like a fragile halo. Expectation versus reality again. Near a quasar that can outshine entire galaxies, theory says the inner regions should be chemically harsh and stripped down, with lighter elements dominating because heavier atoms and dust grains are shattered or blown away by radiation and jets. Instead, JWST's spectra show strong fingerprints of oxygen, carbon, neon, sulfur, and other metals. The ring is not primitive. It is enriched. That enrichment is not subtle. Emission lines from ionized oxygen and carbon are bright, and ratios between those lines point to metallicities at or above the level in the Sun's neighborhood of the solar system. To get that much oxygen and carbon, multiple generations of stars must have already lived and died here, or just beyond this boundary, fusing light elements into heavier ones and throwing them back into space through winds and supernovae. So, near a monster that can sterilize planets across tens of thousands of light years, JWST is seeing the chemical fingerprints of long-running star formation. By the end of tonight, you're going to understand why that is such a problem for current models, because it is not just metals in the gas. The mid-infrared data from MIRI reveal broad features attributed to dust grains and complex molecules, silicate bumps, aromatic carbon signatures. These are the fragile solids that usually live in calmer regions of galaxies, the same kind of grains that eventually clump into planets and shield molecular clouds from ultraviolet light. Yet here they are in significant quantities orbiting a quasar-level black hole. Dust is easy to destroy. Intense ultraviolet and X-ray radiation knock atoms off grain surfaces. Shocks from jets and outflows smash grains into smaller fragments, then into individual atoms. Models predict that close to an active galactic nucleus, dust lifetimes should be short. No one predicts a long-lived, dusty ring sitting in the blast zone. So, something has to give. Either the ring is being constantly replenished by dying stars and inflowing gas, or its geometry provides shielding that current simulations have not captured. Perhaps dense clumps self-shadow, creating pockets where dust can survive. Perhaps the ring is warped, tilting parts of it out of the direct line of fire. Tonight, we're going to treat the ring not just as a victim of the black hole, but as an active player. Chemically, it looks like both a product and a reservoir of star formation, recycling metals and dust, even as the central engine tries to tear them apart. That dual role complicates the simple picture of AGN feedback as purely destructive. And if a ring this enriched can endure here, the next question is obvious. What else is quietly growing in its shadow? So when JWST zooms in on that enriched ring, the surprise is not just what is there, but how it is arranged. No one expects tidy geometry this close to a monster that can sterilize entire star systems. Yet, when scientists model the brightness profile, pixel by pixel, and match it against the measured motions of the gas, a pattern emerges that is hard to ignore. It is not a single ring, it is a nested system. An inner, hotter disk, hugging closer to the black hole, wrapped by a cooler, broader outer ring at the radius where theory said chaos should win. The light is the giveaway. The central region glows more strongly in the infrared continuum, the smooth background from hot dust, while the ring lights up in narrow emission lines from specific atoms and molecules. Expectation, one blurred donut of dust. Reality, a layered structure with distinct zones. Now, let's begin to unpack what those zones mean. In JWST's near-infrared data, certain emission lines, like those from highly ionized oxygen and neon, peak closer to the center, tracing gas that has been blasted by the full fury of the accretion disk and its radiation. In the mid-infrared, cooler dust features and molecular lines flare up farther out, mapping a region where grains can survive, shielded just enough from the central glare. By the end of tonight, you're going to understand why that separation matters. The result is a vertical and radial stratification, hot, dense, rapidly orbiting material inside, cooler, slower, more clumpy gas and dust outside. It looks less like a single smoke cloud and more like a series of atmospheric layers around a planet, each responding differently to the same central source of energy. That pattern interrupt, order inside what should be a turbulent wind of radiation, forces a rethink of how this black hole feeds over cosmic time. Instead of gas plunging straight in or being blown straight out, the data point to a long-lived conveyor belt. Material drifts inward through phases, first as relatively cold molecular clouds in the outer ring, then as warmer, partially ionized gas, and finally as searing hot plasma in the inner disk. Some of it is consumed, some of it is pushed back out. Over millions of years, that cycle can regulate both the growth of the black hole and the fate of the surrounding galaxy. The irony is that theorists already had a name for something like this, the AGN torus, a clumpy, donut-shaped shroud of gas and dust that hides the central engine from some angles and reveals it from others. No one predicts it will crystallize into such a clean, ring-like morphology at this particular radius, with an even hotter, flatter disk nested inside. The classic torus was supposed to be messy, stochastic, a three-dimensional fog. JWST is showing something closer to an engineered structure. And if the disk within a disk is this organized, absolutely no one anticipates what might be hiding inside the ring itself. Could there be embedded star clusters, carving gaps like moons in Saturn's rings? Could compact objects, neutron stars, smaller black holes be orbiting there, unseen, waiting for a collision that would light up space and send ripples through the fabric of the cosmos? The current images do not have the resolution to say, but the hints are there, in subtle clumps and asymmetries along the ring's edge. The most dangerous black hole in this system might not be alone, and the next set of observations is poised to ask a disturbing question. What happens if something inside that ring falls in and the entire structure reacts? So, pause the data. Forget the plots and spectra for a moment. Imagine that question playing out above your head, written across an alien sky. Tonight, we're going to step off the graph and onto a world that almost certainly does not exist. A hypothetical planet buried somewhere inside that glowing ring of gas and newborn stars, orbiting the most dangerous black hole in this system. No one expects a stable planet to survive here. No one predicts oceans, continents, or a calm blue sky. But as a thought experiment, it lets you feel, not just understand, what James Webb has discovered. Look up. One half of the sky is dominated by a single, blinding wound in space. The active core, a point that is not a point at all but a compact glare where the central black hole and its accretion disk compress the light of trillions of suns into something like an artificial dawn. From that glare, twin jets lance outward, narrow and terrifying, painting the sky with columns of ghostly radiance that seem frozen and yet are racing at relativistic speeds. Around you, stretching from horizon to horizon, the ring itself becomes a band of fire, not smooth, clumpy, knotty, dense, star-forming clouds glowing in infrared, braided with darker lanes where dust is thick enough to swallow visible light. It wraps the sky like a warped Milky Way, only far brighter and far closer, a glowing boundary that reminds you that this entire system orbits catastrophe. Beyond that ring, if your eyes could adapt, the host galaxies' spiral arms would hang as faint, ghostly arcs. Patches of blue-white stars, veils of reddish hydrogen emission. They look peaceful from here, like a distant weather system on a calm sea. But every line, every swirl ultimately curves back toward the central engine that is trying to unmake you. The air around this hypothetical planet would be silent, yet the radiation environment would be deafening in every band the human body cannot sense. Invisible torrents of high-energy photons and particles pour out from the core, from the jets, from shock fronts where outflows slam into infalling gas. It is a storm of X-rays, gamma rays, and relativistic wind. Any life would need shielding thicker than mountain ranges, magnetic fields stronger than anything in our solar system, and an atmosphere engineered to turn lethal energy into heat and harmless light. By the end of tonight, you're going to understand why that matters, because in that imagined sky, the fragile glow of star-forming clouds looks wrong. This is a place where gas should be stripped, shredded, sterilized. Yet JWST sees order, rings, clumps, the quiet signatures of creation perched on the edge of annihilation. That mental image is the pattern interrupt in this mission. It makes the data feel as extreme as it really is, and it sets up the real question for scientists. Not whether worlds here are habitable, but how this hostile environment sculpts galaxies and black holes together. Now, let's begin to turn that imagined sky back into measurements, models, and the next round of observations. Now, let's begin to quantify just how extreme this environment really is. To say a black hole is dangerous is poetic. To say it is eating at the Eddington limit is technical. JWST lets scientists bridge those two languages. From the quasar's raw brightness and its spectral energy distribution, they can back out how fast the black hole is actually growing. Measure the luminosity from X-ray to infrared, assume a radiative efficiency for the disk, and the math converts light into mass per year. It is an energy bill that doubles as a feeding log. In this case, the bill is astronomical. The total power rivals or exceeds entire galaxies. When that luminosity is compared to the Eddington limit, the point where outward radiation pressure should nearly balance the inward pull of gravity, it lands right on the edge. This black hole is accreting at or near that limit, growing as fast as physics is supposed to allow without blowing its own fuel away. That regime is famous for turbulence, for wild winds, for feedback that shreds ordered structures. By the end of tonight, you're going to understand why that expectation collides so violently with what JWST actually saw. Near Eddington accretion should mean chaos. Radiation should push on electrons, drag protons along, and launch powerful outflows. Theoretical models predict thick, puffed-up disks, clumpy inflows, and gas blasted into polar funnels. No one predicts delicately nested rings surviving in that crossfire. Yet the infrared images show a ring that is coherent, sharply defined, and laced with what look like smaller, embedded structures. The space around this monster looks more like a carefully tuned system than a demolition zone. That is the paradox. The growth rate screams furious feeding. The morphology whispers quiet order. When a black hole is dumping this much energy into its surroundings, simulations say the nearby gas should be stirred, heated, and stripped. Instead, the ring looks less disrupted than many lower luminosity active nuclei. No one expects the most dangerous object in the frame to be surrounded by the neatest architecture. So, what is going on? One possibility is timing. Perhaps the accretion is episodic. JWST could be catching this system in a bright spike that follows a calmer phase, with the ring preserving the memory of that quiescent period. Or the reverse, the ring may be dense enough to self-shield, letting the innermost flow blaze at the Eddington limit while the outer gas feels only a muted wind. Another interpretation cuts deeper. Maybe the way energy couples to gas near these extremes is different from the standard recipes. If radiation leaks out through channels or if magnetic fields redirect power into narrow jets, large parts of the ring might escape the full blast. That would mean the usual one-size-fits-all picture of quasar accretion and feedback cannot survive contact with JWST's resolution. And if this system is not a one-off, then the next observations will not just refine the models, they will redraw the boundary between growth and destruction around the biggest black holes in the universe. So now the question becomes brutal and simple. If the feedback is that violent, where does anything have room to live? JWST's answer is written not just in the ring, but in what blasts past it. Because once scientists mapped the light beyond the core, they saw something else. Enormous outflows, jets, and winds screaming out of the nucleus, carrying energy thousands of light years into space. These are not gentle breezes. The central engine drives a relativistic jet that shows up as a narrow, elongated spine of emission, and around it, JWST and companion observations pick up high-velocity gas, racing away at hundreds or even thousands of kilometers per second. In spectra, the lines are shifted, split, broadened. This is the black hole's weather report, and the forecast is permanent hurricane. But here is where expectation slams into reality. Early models imagined the feedback as more or less symmetric, a kind of spherical blast wave that just scours the inner galaxy. No one predicts what JWST actually resolves. The outflows are sharply collimated, funneled into cones that punch clean holes through the galaxy's gas along specific directions, while other angles remain strangely, almost eerily, quieter. Picture it in 3 dimensions. Along the jet axis, the system is a blowtorch, carving channels of ionized plasma out into intergalactic space. Within those cones, clouds are shredded, atoms stripped, potential planets sterilized before they ever form. But rotate off that axis by just a few tens of degrees and the violence drops, not to zero, just enough that gravity can start to compete with the wind. That is where the ring comes in. It does not sit just anywhere. It occupies a narrow safe zone in both angle and radius, too close to the black hole and the radiation pressure, and in a wind simply blow the gas out or keep it so hot it cannot cool. Too far out and the material gets swept into the large-scale galactic outflow, accelerated and lost to the system. But in that sweet spot, the flow stalls, piles up, and cools. Before we get started on what that means for star formation, it is worth stressing how invisible this geometry was to older instruments. Blurred by lower resolution, all those cones and cavities collapsed into a single, averaged glow. By the end of tonight, you're going to understand why JWST's sharp vision forces a different picture. Not a simple disk plus halo, but a fully three-dimensional feedback machine, with jets, winds, and sheltered pockets of survival. Now, let's begin to confront the real implication. If this finely tuned safe zone can exist around the most dangerous black hole in the sample, how many other quasars hide similar rings in unresolved pixels? And if those hidden anomalies are common, they are not just curiosities. They could be the preferred sites where new stars ignite and where the next wave of fuel waits, quietly, for its turn to fall in. So let's step back for a moment and look at what this one system is really telling you. Before we get started on explanations and theories, it helps to see the whole pattern at once, like pulling the camera back from a single pixel to the entire image. First, there is the ordered ring itself, a sharply defined, rotating annulus of gas and dust, sitting just a few light years from a black hole radiating near the Eddington limit. Then, layered on top of that, come the signs of star formation right inside that ring, where standard models said the tidal field and radiation pressure should shred clouds before they ever collapse. The space around this monster is not empty chaos. It is building new suns in the shadow of the event horizon. Third, that ring is strangely calm. Low turbulence, narrow line widths, flows that look laminar rather than wildly stirred. In the classic picture, the inner regions of a quasar are a storm, supersonic winds, shocks, clumps colliding at hundreds of kilometers per second. Here, the storm has structure. The wind is being channeled. Fourth, the chemistry is too enriched, too quickly. Heavy elements, complex molecules, and dust grains that usually belong in mature stellar nurseries are showing up in a place that should be dominated by raw accretion fuel. Fifth, nested structures appear when the resolution is pushed, subrings, filaments, and knots that suggest a hierarchy of disks within disks, not a single smooth torus. Sixth, the growth rate does not match the environment. The black hole is shining like it is swallowing fuel at a furious pace, but the resolved inflow through the ring looks throttled, as if the system has found a way to shine near maximum power without gulping material as fast as expected. And seventh, there is that narrow, carved-out safe zone, a low-density cavity maintained by outflows that somehow protect the ring while still letting the mission-scale jets and winds escape into intergalactic space. Any one of these anomalies could have been written off by scientists as a tweak to parameters. Add more magnetic fields here, adjust the clumpiness there, let the simulations run a little longer. But all seven together form a qualitatively different portrait from the simple, chaotic quasar model that dominated for decades. No one predicts a quasar core that looks this organized. Absolutely no one anticipates an almost architectural ring building stars on the edge of a gravitational abyss. By the end of tonight, you're going to understand that your mental picture has already shifted. You are now carrying an image of a structured, star-forming ring orbiting a near Eddington black hole, something that would have sounded like science fiction when the first accretion disk cartoons were drawn, and the stakes could not be higher. If this is not a freak configuration, if similar rings are hiding in unresolved pixels across the early universe, then the standard story of how black holes regulate star formation and sculpt galaxy growth may need a rewrite. Feedback may not just quench, it may carve boundaries where planets and stars can still emerge. Tonight, we're going to push on that tension. Is this system a rare cosmic coincidence, a newly discovered stable configuration, or a sign that our simulations have been missing key physics in the most extreme regions of space? Now, let's begin to test each of those possibilities. To make sense of that impossible ring, you have to zoom out from the black hole's immediate fury and look at the galaxy as a whole. Not the jets, not the glare, the orbits. Because long before gas reaches the event horizon, it has to survive a dangerous journey through the galaxy's rotating disk, where gravity can set up hidden traps. Tonight, we're going to treat that ring as a traffic jam. A cosmic pileup parked at a very specific radius. In orbital dynamics, that kind of pileup has a name: resonance. When orbital periods and gravitational tugs line up just right, material can get herded into narrow lanes or swept out into gaps instead of spreading smoothly through space. You've already seen a quieter version of this in the solar system. Saturn's rings are not just a random smear of ice. Moons like Mimas carve out sharp gaps where their orbital frequencies resonate with ring particles, amplifying tiny tugs into powerful shepherding forces. The result is structure: bright rings, dark gaps, sharp edges, all drawn by gravity's repeating rhythm. Now shift that logic from icy grains around a planet to gas clouds orbiting a supermassive black hole. In a barred galaxy, or a galaxy with strong spiral arms, the rotating bar and the central potential set up resonant radii, where the pattern speed of the bar matches combinations of the orbital and epicyclic frequencies of the gas. At those special radii, the torques acting on the gas can flip sign. Far out, torques from the bar or spiral arms tend to rob gas of angular momentum, pushing it inward. Closer in, the same non-axisymmetric forces can start adding angular momentum instead, trying to fling gas back out. Somewhere in between there is a boundary where the net torque goes to zero. Inflow stalls. Gas that was spiraling toward the center hits a dynamical dead zone and begins to pile up in a ring. By the end of tonight, you're going to understand why many less extreme active galactic nuclei already show these resonant rings. Observations and simulations have discovered nuclear rings of cold gas and star formations sitting near inner Lindblad resonances, acting as bottlenecks in the galaxy's gas supply chain. The galaxy tries to feed the black hole, but the orbital resonances keep intercepting the delivery. No one predicts that same logic would survive unchanged next to one of the most luminous quasars in the universe, yet the geometry James Webb sees around this black hole looks eerily familiar, a sharply defined ring at the radius where simple models say inflow should stall. So, the traffic jam model can explain where the ring forms and why gas might accumulate there instead of rushing straight into the accretion disk. But it leaves a harder question untouched. How does that ring endure in the face of intense radiation, relativistic wind, and violent feedback from the central engine? Before we get started on more exotic ideas, that gap is crucial. Resonance can place the ring, it cannot, by itself, protect it. To explain survival, not just location, the mission now needs additional physics, shielding, self-gravity, and feedback tuned right to the edge of destruction. Resonance can park the ring in a safe orbit, but it still leaves a brutal question hanging in space. How does anything stay cold, molecular and fragile while orbiting a black hole that outshines whole planets, even whole galaxies? Tonight, we're going to lean into an idea that turns the usual picture inside out. Instead of imagining the ring as a victim of radiation, imagine it as an architect. It builds its own fortress, not with walls of stone, but with columns of gas and dust thick enough to swallow light. In simple terms, this is self-shielding. When gas and dust are dense, incoming radiation does not pass cleanly through. High-energy photons slam into grains, electrons, and molecules. They get absorbed, scattered, degraded into lower energy light. The outer layers take the hits. Material deeper inside sees a weaker, softer radiation field, so it does not get ionized, blown apart, or evaporated as quickly. Now, let's begin to picture what that means for this ring. The geometry matters. If the ring is thick, clumpy, and puffed up rather than razor thin, then along many lines of sight, toward the black hole, the column density is enormous. A photon trying to escape from the central engine into the ring's midplane has to plow through cloud after cloud, grain after grain. Each encounter robs it of energy or redirects it. By the end of tonight, you're going to understand why that maze of obstacles can be the difference between annihilation and survival. The result is a natural 2-layer, even 3-layer structure. The surface of the ring facing the black hole is harshly irradiated. There, gas is hot, ionized, turbulent. Molecules are shredded. The spectrum glows with excited atoms and warm dust. But just a little deeper, in the shadowed interior, the radiation field collapses. Temperatures drop. Molecules like carbon monoxide and water can reform and stay intact. In the coldest pockets, dense clumps may even collapse under their own gravity, forming new stars in the very shadow of the event horizon. This is not just theory on a whiteboard. JWST has discovered both blisteringly hot emission and unexpectedly cool molecular lines from the same ring. The spacecraft is seeing signatures of dust at hundreds of degrees right alongside gas cold enough to host complex molecules. Prediction says uniform destruction. Observation shows stratification no one predicts in such an extreme environment. No one expects a black hole's killing field to double as a cradle. Yet the data point that way. If the ring is its own fortress, then the real boundary that matters is not just its distance from the black hole, but the internal architecture of its shield. And that is exactly what upcoming JWST campaigns and high-resolution simulations aim to dissect. Layer by layer, cloud by cloud, until the fortress either holds or cracks. Until the fortress either holds or cracks. But there is a third possibility that almost no one expects. The fortress is being sculpted in real time by the very monster it is supposed to resist. Most galaxy simulations have not been kind to subtlety. To make progress, scientists have had to treat black hole feedback in broad strokes, dumping energy into the surrounding gas either uniformly in a spherical bubble or in clean, simple cones meant to mimic jets. Designed for efficiency on supercomputers that track billions of particles, these prescriptions are blunt instruments. They tend to make feedback look like a cosmic leaf blower. Once it turns on, everything near the boundary gets swept out. But space around a real supermassive black hole is not that tidy. Newer high-resolution models are revealing something stranger. Instead of a steady, all-directional blast, the outflows flicker. They are intermittent, directional, channeled along magnetic fields and into particular phases of gas. Hot, tenuous plasma might be accelerated and expelled, while colder, denser clouds are not simply erased, they are squeezed, twisted, sometimes even shepherded into rings and arcs. Tonight, we're going to focus on that idea of compression. In these simulations, a jet can drill a narrow tunnel through the inner region, venting energy into intergalactic space, while a sideways shock front ripples outward through the galaxy's disk. Where that shock stalls, it can pile gas up at a preferred radius, much like a breaking ocean wave builds a sandbar. The result is a ring that forms not in spite of feedback, but because of it. By the end of tonight, you're going to understand why that matters for this particular quasar. JWST shows an inner zone that looks scoured, a cavity where the radiation and wind from the black hole have clearly done their work. Yet at the ring radius, the gas is dense, star-forming, and astonishingly coherent. The feedback appears tuned, just strong enough to clear out the core and compress gas at that boundary, but not so violent that it unbinds the ring or shreds it into chaos. No one predicts this level of balance by accident, but it does not require magical coincidence. Variability in the black hole's accretion rate naturally turns the power up and down. Magnetic fields thread the disk and funnel outflows into preferred directions. The galaxy's own gravitational potential well sets how hard the wind has to push before gas escapes. Together, these ingredients create a self-regulating system that hovers near a sweet spot, where destruction and creation are locked in a dynamic truce. Now, let's begin to confront the uncomfortable implication. If feedback can be this delicately structured on scales of a few light years, then the course prescriptions in current galaxy simulations may be missing entire regimes of behavior. What happens when those simulations stop using a leaf blower and start resolving jets, shocks, and multiphase gas in detail? Do rings like this turn out to be rare curiosities or the hidden, organizing skeleton of galaxies across cosmic time? Do rings like this turn out to be rare curiosities or the hidden, organizing skeleton of galaxies across cosmic time? Before we get started on grand conclusions, there is an uncomfortable question sitting in the middle of the room. How much of what everyone thinks they understand about black hole feedback is coming from the universe itself, and how much is coming from computer screens? For the last 2 decades, the most detailed stories about how supermassive black holes regulate galaxies have been written not by telescopes, but by simulations. Scientists feed in gravity, gas, dark matter, a prescription for how stars explode, a recipe for how black holes inject energy, and then let the digital universe evolve. The results are powerful. Entire populations of galaxies appear, winds blow out of their centers, and simple rules at small scales seem to explain large-scale structure. But there is a catch. Those rules at small scales are not observed. They are approximated. It is like trying to model a hurricane by averaging over entire neighborhoods. The simulation can track the storm's path across a continent, estimate the total damage, and even predict when the wind will die down. Yet it cannot tell whether a single house on a single street will be shattered or left mysteriously untouched. Now, let's begin the pattern interrupt. JWST's view of this ring is that single house, not a blurred neighborhood, not a smeared-out district in a galaxy, but a sharply resolved structure, only a few light-years from a black hole that blasts space with quasar-level power. In many models, that close-in gas should be shredded, overheated, or launched outward in a continuous, chaotic outflow. No one expects to zoom in and find an orderly ring, dense clumps, and signs that the environment is not just surviving, but potentially nurturing new stars. It is as if the forecast said the entire block was gone, yet the telescope walks up to one address and finds the walls intact and the garden in full bloom. By the end of tonight, you're going to understand why that single, intact house forces an audit of the entire storm model. Because if the small-scale prescriptions for how black hole winds couple to gas are wrong here, they may be wrong in thousands of simulated galaxies that never had the benefit of JWST's resolution. This does not make simulations useless, far from it. They remain the only way to evolve full cosmic volumes to see how planets, stars, and galaxies assemble across billions of years. But simulations are only as good as the physics and resolution put into them. They need anchors. They need ground truth. And that is exactly what this mission is now providing, peering through dust with NIRCam and MIRI to resolve structures that used to be hidden behind a numerical average. No one predicts a single observation to rewrite the textbooks, yet James Webb keeps nudging the boundary. Massive, mature galaxies discovered far earlier than theory allowed. Overgrown black holes already sitting in the young universe when the solar system was not even a dream. And now, a dangerous black hole with a ring that refuses to behave. Tonight, we're going to follow that thread and see how far it unravels our models of how galaxies live and die. So is this ring just a cosmic one-off? A freak accident around one monster, or the first clear example of a whole hidden population? That's the question now driving a quiet but radical shift in how scientists are using James Webb. Before we get started on exotic theories, the community is doing something much more basic: counting. Systematically, astronomers are lining up samples of the brightest quasars and active galactic nuclei across cosmic time, from relatively nearby systems to those that shone when the universe was a fraction of its current age, and pointing JWST at them with the same relentless focus. Same instruments, same filters, same intent. Hunt for rings, arcs, and sharp changes in emission that betray ordered structure where chaos was supposed to rule. No one expects perfect circles in every image. Reality is messier than that. What Webb's infrared eyes are revealing instead are hints, partial rings that glow more strongly at a particular radius, broken arcs that seem to trace the same orbital distance on opposite sides of the black hole, narrow zones where certain wavelengths spike as if a band of gas and young stars has been packed into a cosmic traffic jam. Not every target shows it, but enough to do that absolutely no one anticipates this will remain a single, lonely example for long. Here's the catch: the apparent rarity of these rings may be an illusion born of our old hardware. Previous space telescopes and even the best ground-based observatories hit two hard limits at once. Their resolution blurred the innermost few light-years into a single glowing knot, and their wavelength coverage was tuned to optical light that dust near the galactic center eagerly absorbs. With that combination, any narrow ring would be smeared, dimmed, and effectively erased. Tonight, we're going to lean on Webb's strengths to see past those boundaries. JWST cuts straight through that problem. Its infrared instruments pierce the dust, and its sharp vision can separate structures only tens of light-years apart, even in galaxies billions of light-years away. Suddenly, features that were invisible for decades emerge as clean ripples in brightness, like finding waves on an ocean that used to look perfectly flat. If even a modest fraction of extreme quasars host such rings, the implication is huge. This is not a weird side quest in the story of one galaxy. It becomes a recurring chapter in the co-evolution of black holes and the galaxies that feed them, a phase where feedback and star formation negotiate a temporary truce at a specific radius. By the end of tonight, you're going to understand why that changes the stakes. The question is already shifting from how can this one ring exist to how many galaxies have been quietly growing stars in the shadow of their most dangerous black holes. And if those rings are common, the next step is even bolder, figuring out how long they last and what happens when that fragile balance finally breaks. If that fragile balance can last, it does more than light up a ring. It rewrites the growth chart for the most dangerous objects in the universe. Tonight, we're going to use that quiet, glowing loop to question how fast a black hole is allowed to grow. One of the biggest puzzles in modern cosmology is timing. JWST keeps finding quasars less than 1 billion years after the Big Bang, already powered by black holes weighing 1 billion suns or more. Designed models say growth should be gradual, limited by how much radiation pressure a feeding black hole can push back into space. Reality says some of these monsters bulked up almost overnight on cosmic timescales. To understand why that is so strange, you need the growth speed limit, the Eddington rate. Feed a black hole too quickly, and the light and particles blasting out from the accretion zone push the remaining gas away, like a hurricane wind stripping a cloud bank. The system self-regulates. In theory, that should slow down any attempt to reach those early, enormous masses. Now, let's begin with what a long-lived ring changes. Instead of all the gas diving straight into the event horizon in one catastrophic plunge, the ring acts like a storage disk around a hard drive. Material spirals in, but not all at once. It can sit in orbit, cool, fragment, and then leak inward in controlled streams. The feeding becomes intermittent on small scales, but sustained on long scales. That reservoir effect matters. With a ring, the black hole does not have to gorge in a single outburst and then starve. It can hover near the Eddington limit for longer stretches, always topped up by the ring's supply. No one predicts that a simple geometry change could extend the high-efficiency growth phase, yet that is exactly what this structure hints at. A way to keep the engine roaring without blowing away the entire fuel tank. By the end of tonight, you're going to understand why that is such a big deal for the early universe. If rings like this were common when the first galaxies assembled, they could have turned chaotic infall into organized, ring-fed accretion. That would let black holes in young systems climb the mass ladder much faster, reaching quasar scale before the cosmic clock runs out. But there is a flip side. Rings are not just fuel tanks, they are also cradles. If they cool efficiently, they can fragment into dense clumps and ignite new stars. Every star that forms locks up gas that will never cross the event horizon. No one expects a region this close to a lethal black hole to be a star factory. Yet JWST has discovered exactly that, forcing growth models to juggle feeding and star formation at the same boundary. The implication is clear. To explain those early, massive quasars black hole growth scenarios now have to include ring-mediated feeding, long-term near-Eddington accretion, and the competing drain of rapid starbirth. The next question is obvious. If a ring can shape how fast a black hole grows, what does it do to the galaxy around it? If a black hole can grow inside a star-forming ring, then the reverse is also true. A galaxy can grow stars right on the edge of a gravitational abyss. That means the ring isn't just feeding the monster, it's quietly building the innermost population of the entire system. Now, let's begin with what that really implies. Stars born in these rings don't drift out into the gentle galactic suburbs. They stay in the downtown core, piling up into dense nuclear star clusters or compact bulges crammed into the central few light years. Over billions of years, each ring episode could lay down a new layer, so the heart of the galaxy becomes a geological record of black hole feeding cycles frozen into starlight. Those stars do not live ordinary lives. They orbit inside an extreme tidal field where a tiny change in distance means a huge change in gravity. Their paths can be wildly elongated, tilted, or even retrograde compared to the neat, circular orbits in the disk. Some will be whipped into tight, fast loops, completing an orbit in years instead of hundreds of millions. Others will be pumped to high inclinations, forming a thick, chaotic swarm rather than a flat, ordered plane. Tonight, we're going to push that further, because the gas that makes these stars has already spiraled deep into the potential well. It has been shock-heated, compressed, and enriched by previous generations. That means these central stars can carry unusual metallicities, some extremely metal-rich from recycled material, others oddly metal-poor if fresh, low metallicity gas plunges in from the cosmic web. Mix in bursts of ring activity at different cosmic times, and you end up with age distributions that do not match the calm, extended star formation history of the galaxy's disk. The long-term fate of these stars is even more dramatic. Strong encounters and resonances in the ring can scatter some directly towards the black hole, where tidal disruption events tear them apart and feed brief flares, brighter than entire galaxies. Others migrate slowly inward, bleeding angular momentum and seeding the immediate surroundings with heavy elements, dust, and stellar remnants. Still others are kicked outward, puffing up the central regions and blending ring-borne stars into the larger bulge. If this ring-based star formation is common, it offers a powerful clue to a long-standing puzzle. Observations show tight correlations between black hole mass and the mass, velocity dispersion, and density of the galaxy's central stellar component. No one predicts those relations from first principles, yet if the same inflowing gas both grows the black hole and builds stars in a compact ring, the connection becomes almost inevitable. By the end of tonight, you're going to understand that black holes are not just passive endpoints of stellar evolution. They are engines that shape where stars appear, how central clusters grow, and which regions of space become chemically enriched. They sculpt the very core of galaxies. The next step is to ask, how do these violent central neighborhoods talk to the much larger galactic disk beyond? They talk through feedback, through energy, momentum, and radiation fired from the center into the surrounding space. Now, let's begin by looking at how that feedback has been treated up to this point. In most cosmological simulations, an active galactic nucleus is a kind of emergency brake. The black hole accretes gas, converts a fraction of that mass into energy, and then the code dumps that energy into the nearby medium. Heat the gas, blow it out of the central region, shut down star formation so the galaxy does not grow too many stars too fast. The goal is practical. Make the simulated galaxy population line up with the galaxy masses that astronomers actually see in the real universe. The prescription is simple. Too simple. A few parameters control how efficiently the AGN couples to the gas, how fast it drives winds, how far that energy is spread. Change those, and the virtual cosmos swings from overgrown blue spirals to quenched red giants. But under the hood, feedback in these runs is still mostly a one-way process. Energy goes in, gas goes out, star formation turns off. Then JWST stares at this hyper-luminous, dangerous black hole and finds a ring. Not a shredded, chaotic mess, but a coherent star-forming ring at a particular radius where the outflow and the inflow balance. The radiation and wind from the nucleus do not just expel gas. They herd it. They compress it into a dense lane where clouds can cool, fragment, and ignite new stars in the very region that was supposed to be sterilized. Tonight, we're going to focus on that twist, because this means AGN feedback does not only quench, Under the right conditions, it triggers. It sculpts pockets where star formation is enhanced even as it evacuates or heats gas elsewhere. The same engine that empties the central kiloparsec can at the edge of its influence pile material into a ring that glows in infrared light. This dual role is a problem for simple recipes. A single number for feedback efficiency cannot capture a process that both blows gas away and concentrates it at specific radii. Large-scale simulations that smear AGN energy over tens of thousands of light-years miss the fine structure JWST is actually resolving. The result? Central densities, nuclear star cluster masses, and inner metallicity gradients might all be off in subtle but systematic ways. By the end of tonight, you're going to understand why ring-forming feedback forces model us to rethink how metals are cycled in the inner regions, how long central starbursts last, and how often galaxies build dense, compact cores. No one expects a single JWST image to rewrite decades of cosmological modelling. No one predicts that a ring around one black hole could hint at entire new evolutionary pathways. But if this pattern shows up again and again across different systems and cosmic times, the next question becomes unavoidable. Have simulations been getting galaxy evolution mostly right with a few corrections? Or has JWST just revealed a hidden population of ring-sculpted galaxies that theory never even knew to look for? If this ring is real, stable and common, then the next move is obvious. You go back, you stare longer, you watch it change. Tonight, we're going to push JWST from a snapshot camera into a true ring observatory. The original plan is simple. Take deeper images, gather richer spectra, and see if this elegant structure around the most dangerous black hole in the field holds up under a harsher spotlight. Deeper imaging is the first test. The current data already split the ring from the glare of the quasar, but longer exposures with Narcam and MIRI would drive the noise down and the detail up. Faint knots that now blur together could separate into individual star-forming clumps, shock fronts, or wisps of gas being stripped away. If the ring is stitched together from many tiny segments, not one smooth band, those substructures will start to stand out like lights turning on in a distant city. Then comes the spectral upgrade. With higher signal-to-noise spectroscopy, scientists can track subtle changes in emission lines that trace hot young stars, cooler molecular gas, and the harsh radiation from the central engine. What looks like a single color now could break into a complex barcode of temperatures, densities, and motions. By the end of tonight, you're going to understand why that barcode is the difference between a ring that merely survives and a ring that thrives. But the real shock test is time. No one expects a region this close to a hyperactive black hole to be static. If JWST revisits the system in a few months, then a few years, tiny shifts in brightness around the ring could betray new bursts of star formation, fresh shocks from the quasar's wind, or changing illumination as the accretion flow flickers. A bright knot that flares, fades, and migrates would tell you the ring is responding in real time to the violence at its center. On top of that, astronomers want gradients, not averages, mapping how temperature, gas density, and chemical composition change from the inner edge of the ring to the outer edge, and from the side facing the jet to the shielded side, will test every formation scenario on the table. A smooth gradient suggests slow, long-lived evolution. Sharp jumps, enriched pockets, or metal-poor gaps point to recent collisions, inflows, or partial destruction. To get the full picture, JWST's integral field units become crucial. With NIR spec and MIRI IFUs, each pixel in the ring turns into a tiny spectrum, giving a three-dimensional map. Position on the sky plus velocity along the line of sight. Gas flowing in, gas orbiting, gas blown out by the quasar's wind. Each motion leaves a distinct Doppler signature. No one predicts those flows will be simple. If the velocities are mostly circular and calm, the case for a long-lived, self-shielded, star-forming ring hardens. If they're chaotic, crisscrossed, and multi-layered, then this elegant structure might be a transient accident caught in the act. And absolutely no one anticipates that the answer will be boring, because the next set of tests after JWST may come from instruments that do not look at light at all. Those instruments that do not look at light at all are coming. But before we get started with gravitational waves and exotic particles, there is another kind of vision that has to be brought to the table. Tonight, we're going to give this black hole X-ray eyes and radio ears and see whether the quiet, impossible ring survives under harsher interrogation. JWST lives in the infrared, tracing warm dust and cooler gas. To test the inner engine, scientists turn to observatories that live where the radiation is brutal. Chandra and XMM Newton have been orbiting Earth for decades, catching X-rays from the hottest regions of space, while the planned Athena mission is designed to go even deeper, mapping the million-degree plasma right up against the black hole's boundary. Designed to stare into the glare that would fry normal detectors, these spacecraft can dissect the very regions where theory says the ring should be shredded. X-rays come from the innermost accretion disk, from the compact corona hovering just above it, and from outflows launched at relativistic speeds. Their spectra carry fingerprints of iron atoms whipped around at a significant fraction of light speed, stretched and skewed by gravity itself. Their rapid, flickering, changing on timescales of minutes to hours reveals how clumpy, how turbulent, how structured that inner flow really is. If the inner disk is stable and layered, if the corona is compact rather than bloated, then the violence near the event horizon might be more focused than predicted, leaving corridors where gas can survive long enough to assemble into that outer ring. At the same time, radio telescopes listen for a different story. Arrays like ALMA can pick up the faint glow of cold molecular gas, tracing filaments and clouds that are only tens of degrees above absolute zero, even as the central engine blazes. Very long baseline interferometry networks, the technique behind the Event Horizon Telescope, can map synchrotron emission from jets and compact knots with resolutions so sharp that a solar system would fit inside a single pixel. Where the X-rays show the furnace, the radio shows the fuel lines and the exhaust. Now, let's begin to combine these. JWST draws a detailed infrared map of warm dust, young stars, and shocked gas in the ring. X-ray observatories carve out the geometry of the inner accretion disk, the corona, and the high-energy outflows. Radio interferometers trace the cold inflows spiraling inward and the jets blasting outward, sometimes punching straight through the ring. By the end of tonight, you're going to understand that together they build a multi-phase portrait, from ultra-hot plasma to cold, star-forming clouds, all locked into one feedback loop. No one expects a single telescope to solve a structure this complex. No one predicts that infrared alone can tell where every photon of energy goes. To crack the mystery of why this ring exists at all, the mission has to span the spectrum. And the real test will be what happens when all these data sets are forced to agree or refuse to. That refuse to is where the next experiment begins. Because to really corner a black hole, You cannot just look at the light it spits out. You have to listen to the way it shakes space-time itself. Tonight, we're going to push beyond telescopes entirely and step into the era of spaceborne gravitational wave observatories. The flagship is something that does not look like a telescope at all, the Laser Interferometer Space Antenna, or LISA. 3 spacecraft flying in a giant triangle millions of kilometers across, trailing Earth in its orbit like a ghost constellation. No mirrors, no cameras, just laser beams measuring changes in distance thousands of times smaller than an atom. Now, let's begin with what that geometry buys. Ground-based detectors like LIGO hear the quick, high-pitched chirps from merging stellar mass black holes and neutron stars. LISA tunes into the opposite regime, long, slow waves from massive black holes millions of solar masses across. Whisper quiet inspirals where a compact object orbits a supermassive black hole hundreds of thousands, even millions of times, before finally plunging through the last boundary. Those orbits have a name. Extreme mass ratio inspirals, EMRIs, a stellar mass black hole, a neutron star, maybe even a white dwarf trapped on a tight, decaying path around a monster. Each lap radiates gravitational waves that encode the mass, spin, and warped geometry of the central object with absurd precision. By the end of tonight, you're going to understand why that matters for a ring like the one JWST has just discovered. Because a dense, star-forming ring near a supermassive black hole is not just a pretty structure. It is a factory for compact remnants. Massive stars live fast, die young, and leave behind black holes and neutron stars. Pack thousands of those stars into a narrow band, stir them with strong gravity and violent winds from the active nucleus, and collisions and captures become inevitable. Tight binaries form, harden, and either merge with each other or get flung onto orbits that dive toward the central black hole. From the outside, that looks chaotic. From LISA's perspective, it is a symphony. Each inspiral in the heart of the ring would send out a distinct gravitational wave track, slowly sweeping in frequency over years. Some signals would come from compact objects still embedded in gas and dust. Others from bodies that have just escaped the ring and are skimming the inner accretion flow, tracing out the warped space-time right above the event horizon. Before we get started on how to combine those views, notice the contrast. JWST gives an infrared map of where the gas is, where the stars are being born, where the dust glows under the black hole's radiation. LISA would not see any of that light. Instead, it would reveal how many compact objects actually survived, how often they fall in, and exactly how the central gravity well is shaped. No one expects a star-forming ring in such a dangerous environment. No one predicts that the same ring could become a catalogue of doomed compact objects, each writing its own death spiral into space-time. Yet if both JWST and LISA lock onto the same system, the mission changes. It stops being just an image of an impossible ring and becomes a laboratory for strong gravity, stellar evolution, and feedback in the most extreme conditions the cosmos can offer. And absolutely no one anticipates the sensory twist that follows, because if that happens, astronomers will not only see the ring around this black hole, they will, quite literally, hear the deaths of stars within it as ripples in space-time wash through a silent triangle of spacecraft far beyond our own solar system. So, at this point, the temptation is obvious: a perfect ring near the most dangerous black hole in the field of view. The mind jumps straight to exotic new physics, a forbidden orbit, a new phase of matter, a cosmic halo no one predicts. But before we get started rewriting the laws of gravity, scientists do something much less glamorous and much more powerful. They ask a brutally simple question: are we misreading the signal entirely? The most conservative camp argues that the ring might not be a ring at all. In their view, James Webb is looking through a tangled, three-dimensional mess of gas, dust, and stars. Project that chaos onto a two-dimensional detector, and the human brain will happily trace clean circles where only arcs and clumps exist. A warped accretion disk, twisted by the black hole's spin, can tilt different annuli toward the spacecraft, brightening a narrow band that only looks like a closed loop. In simulations, these warped disks can mimic rings frighteningly well. A puffed-up inner torus, a thinner outer layer, and a sharp temperature gradient can all conspire to create a luminous edge when viewed at just the right angle. But there are signatures that betray the illusion. The velocity field should shear smoothly with radius. The spectrum should change gradually with distance from the center, not snap into a narrow, uniform band. And the polarization of the light, twisted by magnetic fields and scattering, should reveal a flared, three-dimensional structure rather than a razor-thin geometry. Others push a different conservative idea. Perhaps this is not a disk at all, but an outflowing shell driven by the black hole's radiation. Think of a spherical shock front where the quasar wind slams into denser gas. Viewed from far beyond our own solar system, a glowing shell can project as a bright ring, like looking at the edge of a soap bubble. In that case, the velocities should point mostly outward. The line widths should be broad and turbulent, and the temperature should fall off in a way that tracks a blast wave, not a stable orbit. Then there are the more speculative whispers. Maybe the ring traces an unusual distribution of dark matter, compressing normal gas into a narrow band. Maybe the accretion physics near these extreme black holes is entering a regime standard models never anticipated, with radiation and magnetic fields locking gas into a new quasi-stable configuration. Tonight, we're going to entertain those ideas, but only with a warning label. The current data do not require exotic matter or new forces. The ring interpretation wins for now because it explains more with fewer assumptions. By the end of tonight, you're going to understand why that caution matters. In science, multiple working hypotheses are not a luxury. They are armor. Every alternative projection, warped disk, expanding shell, dark matter caustic becomes a stress test. The ring must survive. If it passes, the cosmos has just revealed a new, stable architecture perched on the very boundary of a supermassive black hole's reach. If it fails, then something even stranger is hiding there, a geometry no one expects, and absolutely no one anticipates, and the next observation is about to expose it. So now the question becomes unavoidable. If that ring survives, what does most dangerous black hole even mean anymore? At the start, it was easy to picture this object as pure annihilation, a gravitational executioner at the center of a galaxy. But James Webb has forced a rewrite. Danger here is not just about what the black hole destroys, it is also about what it shapes, sculpts, and, under extreme conditions, quietly nurtures. Tonight, we're going to hold both images in your mind at once. On one hand, a central engine feeding it close to its Eddington limit, blasting space with radiation and plasma, driving a wind that can strip gas from whole regions of the host galaxy. On the other, that same engine carving out cavities with jets and shocks, while a narrow, shielded ring just beyond the worst of the glare calmly accumulates cold gas and turns it into new stars. The monster is also a midwife. By the end of tonight, you're going to understand this as a layered system, not a single lethal sphere. At the absolute center is the event horizon, the one boundary nothing crosses twice. Just outside lies the inner accretion disk, where magnetic fields whip gas into a luminous maelstrom and launch relativistic jets. Farther out, dust condenses into a thick torus, absorbing high-energy light and re-radiating it in the infrared where Webb's instruments can see. Beyond that torus, in a razor-thin annulus, the star-forming ring orbits like a protected lane on a cosmic highway, and beyond even that, the outer galaxy soaks up the feedback. Each of those boundaries hosts a different regime of physics and a different role in the life of the galaxy. Close in, the black hole sterilizes. Any nearby planets would be bathed in X-rays and particles. Whole solar systems could be stripped or erased. But at the ring, the same pressure that evacuates cavities also compresses gas clouds just enough to collapse. The destructive outflow becomes a trigger, turning chaos into order, radiation into the birth cry of new suns only a few light years from the event horizon. No one predicts that the most luminous, violent cores would be the ones quietly seeding stellar nurseries at their hearts. Yet, that is the mental model Webb is forcing on scientists. A feedback engine that can quench star formation across tens of thousands of light years, while simultaneously igniting it in a tiny, hidden sanctuary right next to the black hole. So, when you picture this environment now, it is no longer a single black sphere eating everything in reach. It is a dynamic ecosystem, stratified in rings and shells, with sharp transitions and surprising safe harbors. The next step is to ask how stable that ecosystem really is, and what happens when the balance between danger and creation finally breaks. That balance between danger and creation is not just a local curiosity, it is a time machine. Because when James Webb stares at this most dangerous black hole, it is also looking back more than 12 billion years into an era when the first large structures in space were still assembling. Before we get started on the implications, remember what JWST has already discovered out there. Compact, blindingly bright galaxies less than 1 billion years after the Big Bang, black holes with masses of hundreds of millions, even billions of suns, already in place while the cosmic clock is barely ticking. Designed models say growth should be slow and fragile. Reality says some objects went from zero to monster in record time. Tonight, we're going to connect that mismatch to the ring. Because if one extreme quasar can maintain a dense star-forming ring right next to a lethal engine, maybe this is not an exception. Maybe it is a blueprint. In that case, ring-mediated accretion is not a side effect. It is a fast lane. Here is the idea. Gas falls in from the galaxy, slams into the ring and stalls. Friction and shocks in that narrow zone turn orbital energy into heat and turbulence. Part of the gas drains inward, feeding the black hole more steadily than chaotic clouds could. Part of it fragments, cools, and forms stars in a tight, central population. The same structure that looks like a sanctuary is also an accelerator for both black hole growth and the birth of new suns. By the end of tonight, you're going to understand why that matters for the entire early universe. In the first billion years, the cosmos is transitioning from neutral and dark to ionized and transparent. That process, rionization, needs intense radiation sources. Quasars are obvious candidates, but a star-forming ring wrapped around a quasar concentrates thousands of massive, short-lived stars in a region that is excellent at venting energy, metals, and wind into space. Those winds do not stay local, They push out into the young galaxy, enriching gas with heavy elements that future planets will need, and punching channels where ionizing light can escape into the intergalactic medium. No one predicts that the most efficient reionization engines might be these compact, ring-dominated cores, yet JWST is forcing that possibility onto the table. Now, let's begin to zoom out. Many of the high redshift galaxies JWST sees look like tiny, bright knots, with almost no extended disk. One interpretation is that the entire galaxy is just small. Another is that the central few hundred light-years are doing almost all the radiating. If rings like this are common, some of those compact galaxies may be dominated by light from the ring and its newborn stars, not from a mature, sprawling system. That means a single, most dangerous black hole, dissected in detail, can ripple outward through cosmology. It changes how scientists reconstruct the growth of galaxies, the timeline of reionization, and the way the early solar neighborhoods of the universe were seeded with metals. No one expects one target to rewrite the opening chapters of cosmic history, but absolutely no one anticipates how far this one might go. The next question is whether the ring can survive its own success. The ring can change history. But to feel what that really means, you have to put this monster next to something familiar. Start small. Start with the sun. The black hole James Webb is staring at can blaze with the power of 1 trillion suns. Not 1,000, not 1,000,000, 1 trillion. If the sun is a single household light bulb, this quasar is a continent lit up edge to edge, every city, every street, every window on at once. And that single, furious point outshines entire galaxies. Compare it to the Milky Way. All the stars in our galaxy together produce maybe a few dozen billion suns worth of light. This one active nucleus can rival or even exceed that total. One compact engine smaller than our solar system radiating as much energy as hundreds of billions of stars spread across 100,000 light-years. No one predicts that kind of imbalance the first time they hear it. Now stretch the scale in time. This quasar sits billions of light-years away. The exact distance depends on the target, but the look-back time is the key. The photons hitting JWST's mirrors tonight left when the universe was only a fraction of its current age, when young galaxies were still assembling, when the cosmic web was just starting to glow. By the end of tonight, you're going to understand that this is not just a distant object, it is a fossil beam from a much younger cosmos. Pattern interrupt. If a system like this is so dangerous, how are viewers calmly watching from a blue planet wrapped in a thin atmosphere? Because our own galactic center is quiet by comparison, the Milky Way's central black hole, Sagittarius A, is millions of solar masses, not billions, and it is underfed. It flickers, it sputters, it does not roar. The solar system orbits tens of thousands of light-years out in the galactic suburbs, far beyond the harsh radiation cones that would sterilize planets, near a raging quasar. Tonight, we're going to use that contrast as a mirror, shift the initial conditions just a little, pack more gas into the early Milky Way, spin up the central black hole, and this galaxy could have followed a very different evolutionary track. The same physics that built the ring Webb discovered might have been turned up to extremes here, flooding our sky with deadly light instead of gentle starlight. From this calm perch, with a stable sun and a relatively mild galactic wind, a species can build telescopes, launch spacecraft, and aim infrared eyes across the boundary of time. Now, let's begin to treat that as more than coincidence. It is a position of privilege in space and history, one that lets scientists watch distant storms and decode their secrets without being consumed by them. From that safe distance, the view feels sharp. The ring is there, the black hole is blazing, the surrounding galaxy glows in infrared. But even with James Webb's power, what you're seeing is still a blurred sketch, not a finished portrait. Individual stars vanish into a smear of light. Compact objects hide inside single pixels. Fine substructures dissolve into a soft halo. Tonight, we're going to lean into that blur because the unresolved parts might be where the real danger and the real surprises are hiding. JWST can pick out features within a few light years of the central monster, which is astonishing. Yet for a system that spans thousands of light years, that resolution is only the first rung on the ladder. The ring that looks so clean in the processed images could, at finer scales, be anything but simple. Future instruments change the game. Extremely large telescopes on the ground will stitch together mirrors 30 or 40 meters across. Space interferometers could fly multiple mirrors in formation, turning separate spacecraft into a single virtual eye the size of an entire orbit. By the end of tonight, you're going to understand that what JWST has revealed may be the low-resolution version of a far stranger reality. Zoom that ring up with those future eyes and the smooth band might fragment into clusters, gaps, and spiral patterns like a planetary ring system scaled up to galactic proportions. Bright knots could mark pockets where stars are forming on knife-edge orbits. Dark gaps could betray embedded black holes or dense clumps of invisible matter, carving lanes as they plough through the gas. No one predicts that a region bathed in such brutal radiation would host a delicately sculpted ecosystem of structures, but that is exactly what the data are beginning to imply. And that visible ring may not even be the whole story. Closer in, hidden under the glare of the accretion disk, there could be additional, tighter rings, twisted streams, or warped spirals feeding the beast in layers. Think of a nested network of conveyor belts, each one operating at a different speed, each one vulnerable to disruption, yet somehow persisting long enough for JWST to catch this single frame. That raises questions that cut across galaxy evolution. How stable is a ring like this over millions of years? Does it survive multiple outbursts from the central engine, or is this a brief, precarious phase? How often do such rings form and dissipate across the population of active galaxies? And when they vanish, do they leave scars, fossil gaps, starburst rings, or warped stellar disks imprinted on the host system long after the gas is gone? Before we get started on those answers, it's worth remembering something about astronomy. The first impossible thing you see is rarely the last. JWST has caught one glimpse of a ring that should not be there, balanced on the edge of the most dangerous black hole in its field of view. The real question is what else is hiding just beyond our current resolution, and what happens when the next generation of telescopes finally brings those shadows into focus. So, step back for a moment and replay the whole journey. At the start of tonight's mission, this most dangerous black hole was just a single, blinding pixel in the sky. A point so bright in space that even powerful telescopes saw only glare. No structure, no context, just a quasar that outshone its entire host galaxy and threatened to erase any detail hiding near its core. Then James Webb changed the rules. With infrared eyes that cut through dust and a mirror sharp enough to resolve features just a few light years across, JWST turned that pixel into a landscape. What looked like a featureless beacon became an organized system, jets, dust, and most shocking of all, a ring of stars calmly orbiting inside the radiation field that should have torn them apart. Expectation said 1 point. Observation revealed a ring. That ring is the paradox in its purest form. In a region where theory predicted only chaos and destruction, there is structure. Where the equations said gas should be stripped, shredded, and blown beyond the galaxy by a furious wind, JWST sees chemistry rich enough to assemble complex molecules and clouds dense enough to collapse into new suns. No one predicts stellar nurseries on the doorstep of a quasar, yet the data show exactly that kind of behavior. By the end of tonight, you're going to understand how deep that shift really runs. Black holes no longer sit in the story as simple cosmic drains. They emerge as engines that both destroy and create, shutting down star formation in one direction while apparently igniting it along carefully sculpted paths. Feedback stops being a single on-off switch and starts to look like a layered conversation between the black hole, its accretion disk, its jets, and the galaxy wrapped around it. The center is no longer a void, it's an ecosystem. There's the relativistic core where space and time are twisted past recognition. There's the bright accretion flow where magnetic fields tangle and launch jets. There's the dusty torus that hides and reveals the heart of the system depending on angle. And now, astonishingly, there is a star-forming ring threading that chaos, marking a new boundary between annihilation and survival. Across this video, 7 discoveries locked that picture into place. The resolved ring itself, the unexpected cold gas near the core, the surprising stability of orbits in a region of tidal violence, the chemical fingerprints of active star formation, the way the quasar's light both strips and compresses nearby clouds, the mismatch with standard accretion models, and the implication that this might be common, not rare, among active galactic nuclei. Together, they force scientists to refine how black holes grow, how their feedback sculpts galaxies, and how our own cosmic neighborhood might once have looked. Before we get started on the final question, what this means for the future of black hole astronomy, recognize what you've gained. You can now explain why James Webb's look at this most dangerous black hole revealed something that shouldn't be there, and why that single impossible ring may redraw our map of the universe. So step back for a second and look at what it took to reach that conclusion. A single clean ring of light around a distant, dangerous black hole sounds simple. It is anything but simple. That ring is the end product of decades of engineering, international collaboration, and patient observation. Thousands of people on Earth working across languages, budgets, and generations to give one spacecraft the power to see through cosmic smoke. James Webb is not a lucky snapshot. It is a 6.5-meter mirror, unfolded in perfect alignment, cryogenic instruments chilled to a fraction of a degree above absolute zero, and a sunshield the size of a tennis court, balancing in deep space. It stares through the dust that hides active galactic nuclei, resolved structures within a few light-years of black holes that outshine entire galaxies, and translates that infrared glow into data scientists can actually understand. No one expects a ring like this to fall out of the noise. No one predicts the universe to hand over an impossible signal so cleanly. And yet, this is still the beginning. Webb has years of cryogenic life left. The most unsettling, model-breaking discoveries may not sit in the images already released, but in the data that has not even been downloaded yet, waiting as raw numbers in a deep space buffer. Somewhere in that river of photons could be another star-forming ring where radiation should strip every atom, or a black hole wind that behaves like nothing in the standard playbook. Now, Let's begin the part that continues after the video ends. Picture James Webb, a single spacecraft hanging beyond the planets, at L2, staring into darkness. Its mirrors collect photons from impossible structures, a ring of light encircling a black hole that should only destroy. On a small planet far away, people gather around screens, choose to keep looking, keep questioning, and keep being surprised. Absolutely no one anticipates where the next impossible signal will appear. So, what do you do with a ring that shouldn't be there, quietly orbiting the most dangerous black hole in sight? You add it to a long, messy, glorious tradition in astronomy, the tradition of the universe refusing to follow the script. Before we get started on what this means for you, zoom out in time. Quasars themselves were once a problem, not a solution. Radio sources with star-like points of light, redshifts that made no sense, luminosities that blew past what any normal galaxy could produce. For a while they were just quasi-stellar objects that broke the charts. Pulsars arrive next, radio beacons ticking with a ridiculous precision, so strange that the first detection paper half-jokingly labelled them LGM, for Little Green Men. And then there is dark matter, a silent gravitational pull discovered because galaxies and clusters spin and move in ways that visible matter alone cannot explain. No one expects those anomalies to become the backbone of modern cosmology. No one predicts that the weird outliers will define how space, time, and structure in the universe actually work. Yet that is what happens, over and over. Tonight, we're going to treat this star-forming ring the same way. At first glance, it looks like it violates the rules. Intense radiation, relativistic jets, and a furious accretion flow should scour the region clean, not cradle new stars. But shouldn't be there in science almost never means impossible. It usually means doesn't fit the current models of how this system behaves. The work of scientists, from the first quasar spectra to James Webb's infrared images, is to turn that mismatch into a new, richer picture. Prediction versus observation. Theory says extreme black holes blow gas away. JWST discovers islands where gas cools, collapses, and ignites. Models say star formation shuts down near that boundary. Webb's instruments reveal rings that glow with newborn clusters. The laws of physics do not break. The understanding of how those laws play out in the most violent environments expands. Pattern interrupt. This is not just about galaxies, it is about how to think. The universe is under no obligation to be simple, to match the first simulation, or to respect anyone's favourite diagram of an active galactic nucleus. By the end of tonight, you're going to understand that "this can't be real" is often just the first draft of "this is more complex and more beautiful than expected." The same mindset scales down to everyday life. A belief about how people behave, how a career must unfold, how a relationship or a mission should work, meets data that does not fit. The easy move is to ignore the anomaly. The scientific move is to ask what model needs to change so that the new observation is not an exception, but a clue. Now, let's begin to push this further and see what happens when many such impossible rings start to show up across the cosmos. Now, let's begin to pull all of that into a single frame. Picture the core of that distant galaxy one last time. The jets, the shock fronts, the radiation wind that could strip the atmospheres from entire planets in a heartbeat. At the very centre, a gravity well millions or billions of times the mass of the Sun. A black hole so dangerous that no one expects order to survive in its immediate neighbourhood. And yet, there it is. A thin, glowing ring of gas and young stars calmly orbiting right next to the engine of destruction. It hangs there like a halo drawn with a single stroke of light, suspended on the knife edge between falling in and flying apart. Designed by theory to be a maelstrom of chaos, discovered by a telescope parked in the cold shadow of Earth as something unexpectedly precise. That ring sits on multiple boundaries at once. It marks the frontier between order and chaos, where gravity and feedback wrestle every second for control of the surrounding space. It stands between creation and destruction, where the same black hole that can unmake solar systems also compresses gas enough to ignite new stars. And it lies right on the edge between the physics scientists understand and the questions that absolutely no one anticipates. From here, that entire galaxy is just a point of light. The spacecraft that revealed this ring never leaves Earth orbit. It simply unfolds, cools down, and opens its mirrors to the infrared sky. Yet from a million miles beyond the planet's dayside glare, James Webb can thread its vision through curtains of dust, separate starlight from jet light, and begin to read the story written in that impossible orbit. The contrast is almost absurd. A telescope with segmented mirrors and gold-coated glass operating at a few tens of kelvins, quietly mapping the behavior of a black hole that can outshine trillions of suns. A ring only a few light years wide, redefining how a whole class of galaxies evolve over billions of years. Before we get started on the next generation of missions, this alone is enough to show how far the system of human curiosity has already reached. By the end of tonight, you're going to understand one more thing. This is not the only edge out there. The universe is full of rings, shocks, and boundaries, from the heliopause carved by the solar wind to the event horizons of supermassive black holes. Every time a new instrument crosses one of those thresholds, reality comes back stranger and more beautiful than expected. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.